You're on. You through Manchester anyway. But altogether,
Great.
yeah, you have to change most of the time.
Good morning. Welcome back to MACSMIN 2026. It's a great pleasure to introduce our guest from the US, Professor Alex Wlodawer, who will talk about community efforts to improve the contents of the protein data bank. So over to you, Alex.
Okay, thank you. All right, so protein data bank. Come on. I thought that it should work. Now it works? Okay. All right, so that is the top page of the protein data bank RCSB. So that's the US version of it. Of course, for those of you who don't remember the history of protein data bank, it was established in 1971 with 7 structures of proteins. And I remember times when you were sending 9-track tapes to Brookhaven, and then you were getting 9-track tapes from them. And those were the structures. I mean, things have changed since then. So right now we have about 250,000 structures, plus more than 1 million of structures from AI. And it's really a very important resource. However, the question is whether everything in the protein data bank is perfect, and there is no such thing as perfect in science. And so there is this bunch of people that I belong to that look at contents of protein data bank and try to find things which are not exactly the best, and but the idea is not just to criticize, but to improve. That's what we aim for. Okay, so you told me.
Yeah, sometimes.
Okay, it's here.
Yeah.
Okay, so what can we say about it? There are some problems with some of the structures that are deposited, and right now, of course, when you deposit a structure, you get a validation report. So protein data bank uses all sorts of software to verify that the structure is at least in agreement with data and agreement with what you know about geometry of macromolecules. But if the depositors decide to disregard it, then they disregard it. And one of the things which was found here is the question of duplicate entries, and that was quite a lot of fun collaborating with the Liverpool group here on it. And of course, the major change right now is that in the last decade, the cryo-EM became the important part of structural biology, and I'll be talking about it near the end of my talk. Oops, I went too far.
It's a bit. I went too slow.
I went back. Okay, so the question is, are the structures always correct? So this is, of course, a classic of Carl Brandin's statement. One of these models is clearly wrong. That was the famous case of Rubisco that David Eisenberg's group traced exactly backwards. And of course, that is no longer a problem, that type of problem. Now, I cannot say that I was not guilty of some of these things, because the structure of asparaginase that we first published was only 80% wrong. We did manage to trace 20% of the chain in the right direction. Now, to justify even the sequence of that enzyme was not known at that time. And miraculously, we traced, as I said, most of them incorrectly, 331 amino acids, which turned out to be the right number of amino acids, not because we knew what we were doing. But, so these are the types of problems that used to be in the past, but that really is the past. So that's history. And we corrected it. Now, the one aspect of it that I want to stress in this particular case is that even though the structure that we quote unquote solved as asparaginase was wrong, it was not useless, because 5 years later we used this particular structure, or really the shape of the molecule, without any detail of how it was fitted, in order to help us to find heavy atom derivatives for another asparaginase from a different source. And in that case, we managed to solve it correctly, but it was help. So as long as it was not taken as a real structure, it was useful. Wrong, but useful. So here is something that is very current work. And of course, since I am at NIH and I am on vacation today, I am not supposed to talk about my current work. So please, you didn't hear that this is what we're working on. But one of the things that I was really puzzled about is why there are more than 1,000 structures of hen egg white lysozyme in the protein data bank. Now, you see here some statistics. So these are all structures of the same enzyme, 129 amino acids, very simple. You see the structure in here. There are structures in different space groups. There are structures which are atomic, truly atomic resolution of 0.65 angstrom. So why do we need 1,200 of them? And is it a plus or a minus to have that many? So we started looking at them. And here is one of the important things about validation reports, because validation reports, for those of us who don't want to go into details, gives you a graphical description of what they think about at least some quality of the structure. And here you see two structures of lysozyme, which I call the best and the worst. Telling the truth, the best is the best, but the worst is not the worst, but it's the worst structure for which all of the data are available. And you can see that for the worst one, everything is in the red, which means that both are free, which is an indicator of how well the model agrees with the diffraction data. And all of the geometrical parameters like clash score, Ramachandran, and sidechain outliers, and so on, are all in the red. And the last parameter here is the agreement between local electron density and the model, the RSRZ. So you can see that in this case, everything is very bad. And in the other one, everything is completely ideal. It's completely ideal as structure. So, of course, the thing that we realized is that many of those lysozyme structures were used for methods testing. And so actually, the reviewers were questioning us, so if you're saying that most of them are for methods testing, so can you identify all of those methods testing structures? And the answer is no, we cannot, because unless the authors said that it's for methods testing, we wouldn't really even know. And also, in many cases, they were not published. They were deposited but not published. And it's the famous to be published indicator in the protein data bank, which translated into plain English means never to be published. Come on, baby. Okay, so one of the things, again, of our disagreement with the reviewer is this slide, because being a very simple-minded person, I thought that there should be a very simple correlation. Quality of the structure should be correlated to quality of data. So quality of data, okay, one of the parameters for the data quality is simply the merging R factors, how well the internal consistency of the data works. And one of the indicators, and these are of course not all, for the quality of the data of the structure, is the R3, which means the R factor calculated for the subset of reflections that were not used in refinement. And the hypothesis was that there should be correlation, and the result is that there isn't any correlation, any significant correlation. So the reviewer of our paper, one of the reviewers, said, that's a trivial answer. And my answer is no, it's not a trivial answer, it's a negative answer. But it was a positive hypothesis. We made a hypothesis, it turned out that it was a wrong hypothesis, but this is valuable, I think, still. So we're still fighting. The paper is not yet accepted, but we'll see whether it will be. Oops. Okay. What is it that it's going very well, going up, but not going down. Okay. All right. So in those structures of lysozyme, there are some cases you see on the left here of very careless modeling. You can see two residues, asparaginases, aspartic acid, which clearly do not like the way they were modeled, and there is a very nice density on the bottom. For the asparagine, there is not so nice density for the, for aspartic acid. There is not so nice for asparagine, but with a little bit of re-refinement, you at least get a model in which you don't get a perfect fit, but you're not fighting the density. So the point here is that when people, that was one of the structures used for methods testing, and fairly high resolution structure, and people, once they tested their method, they didn't really bother to do the proper refinement. Well, okay. Now, how careless can you be? Usually we know that covalent bonds are not 0.3 of an angstrom. So why should we leave such things in your structure which will deposit in the PDB? And the answer is because you do not care. But of course, this is already pollution of good database. Okay, so the one question is, can we come up with some kind of an overall descriptor of the quality? And there are people who came up with something called PQ1, which is a indicator merging the quality of the data with the quality of the refinement, and you can argue a little bit about relative weights of various components. So PQ1 you have to take with proper level of skepticism, but at least if it's done in the same way for all structures, it does give you some indicators. So you can see, for example, that those structures of lysozyme on the average, and PQ1 should be 1 for perfect structure and 0 for perfectly wrong structure. So you can see for the lysozyme, both the means and median PQ1 values and also the values of R3 are worse than the average. So the take-home lesson is that this huge bunch of structures, which were used mostly for methods development, are on the average worse than the average. Okay, all right. So there is one answer here. Now, on the other hand, we looked already at another group of proteins. It's a little bit smaller group, but there are about 200 deposits of protein kinase A. And these structures were determined mostly for the purpose of really learning about those molecules under different conditions with different drugs. So those were very much question-oriented structure development efforts. And as you can see here, in this graph, for the very poor values of PQ1, clearly these structures are better than average for all the structures in the PDB. And for the best ones, they are also better. So there are more of the high PQ1s than the average and less low PQ1 than average. So in this particular case, we can really trust the PDB much more because the average quality of these structures is definitely better. And here you see again those indicators for the best and the worst structure. Now, the best structure is not as good as the best lysozyme structure, but that, of course, is because lysozyme was the best structure was at 0.65 angstroms, and the best structure of pKa is, if I remember correctly, around 2 angstroms. So it's not as accurate, but also you can see that the worst structures is not as bad as some of the lysozyme structures. So there is a lesson here. Now here we come to this work with Vitaly and the group about duplicate structures. Now, it never came to our minds even to question whether there are duplicates in the PDB, because of course there aren't any such things as duplicates, until those mathematicians decided to try some weird methods of looking for duplicates. And it turned out that there were quite a lot. This is not by no means the complete list. And this is just a partial at the top of the table in our paper. And one of the things I want to show in here are the structures. You can see on the bottom a duplicate where I was questioned, how come a duplicate is duplicate of itself? What's the meaning of it? And I was asked this question last week because I gave this talk to my colleagues at NCI, and you know, they have very, very good eyes, much better than I, and they pointed out that that doesn't make any sense. Yes, it doesn't make any sense but it was not done by sensible people, because what that particular structure, there are two of those, have is a PDB file in which the same molecule is in the same place twice, superimposed on itself, which would not be a crime if it weren't for the fact that it's at the full occupancy. So in other words, the structure has the occupancy of 2. And, you know, at one time when I was in the army, we were taught that under battle conditions, cosine can go above 1, but it's only in the military. But occupancy also should not go above 1. And they did some tricks which are simply disallowed tricks. And I know what they were trying to do, but they came up with this duplicate. Now, most other structures here are real duplicates. There are 2 structures with different PDB codes and identical structure. You know, PDB knows about it. That's the good news. PDB did nothing about it. That's the bad news, because all of these other structures should either have been removed or at least somehow marked. Now, there is something called group depositions. There is a program called PanDDA, and that's a very valuable way of looking for very poorly occupied sites for small molecules. It's used for drug design. The problem is what happens when these structures are deposited in the PDB. And as you can see here, there are some examples of these structures which have absolutely the worst possible descriptors. But that's because those maps in PanDDA are not really corresponding to what we understand as electron density map for a particular data set. They use 200 data sets to calculate the map. And of course, if you compare it to only one of them, it will not compare perfectly. So our suggestion to PDB, again, was to somehow either mark them very, very clearly or to put them into some subdirectory of PDB because they are very valuable, but they should not be mixed with individually determined structures. By the time my grandchildren will retire, maybe PDB will do something about it. Okay, another question. Are waters important? And our point is that, you know, waters might be quite important, especially in a structure which was determined at subatomic resolution, you know, 0.89 angstrom. The paper describing that particular structure is talking, as you can see, the title of the paper about water networks, and yet the coordinates in the PDB don't have waters. Clearly a problem with what was deposited. And as you can see, if you do some calculations using the deposited data and deposited map, you know, absolutely perfect waters, those famous pentagonal arrangements of water molecules and so on are all there, but not in the deposited coordinates. And we did some analysis, and I don't want to go into it very much, but if you look at the B number, the panel B here, you can see that we did statistically calculate how many water molecules can you expect in each structure on the average. And of course, that depends very much on the resolution of data. And you find that on the average, for atomic resolution structures, there might be about 3 water molecules per 1 amino acid. You know, at 3 angstrom structures, you can barely see any solvent, and then everything in between. So I think, again, this type of analysis is valuable. It might not be the most important stuff, but it's good to know. So again, the question of waterless structures. So there are some structures with beautiful density, and there is no surprise that in the middle, in the core, in this case, you don't see much solvent. But if you don't see solvent out on the surface, then there is something peculiar about what was deposited. Now, this was a little bit of a problem. I stumbled into that structure because in this case, you can see beautiful waters. They are all in completely red density. Red means negative density, which means that they are in the model and not in the data. And in this particular case, I believe there were 19 water molecules in the model, and all of them were of the quality that you see here. And it's that was the published structure. I don't want to be too brutal, but I think that this is a case of manufactured structure and not a real structure. And we were in contact with the corresponding author of this paper, who said that he knows nothing about the quality of structures because that was done by his colleague, the other author, and the other author was kind of unwilling to talk too much. And there are a number of structures from these two gentlemen in the PDB. And I think that after the infamous Krishnamurthy case of 15 years ago, when there were about a dozen of manufactured structures deposited in the PDB, and which were all fake, I think that these come about as close to being fake and poorly faked, because, you know, at least if you fake it, you should have some agreement between your fake data and fake model. And that's not the case here.
Crystal structure prediction. What is very strange, when you look inside the PDB file, or the MCF, there is for the water, the B factor is supposed to be of good quality.
Yeah. Okay. If you fake it, you can always fake B factors.
But with the same B factor value for every molecule. Like copy paste.
So here you can see another case where you can see some very nice densities for waters that for some reasons the authors decided not to model. I don't know why. And, you know, and there is something about that, because I remember that during the COVID pandemic, there were lots of structures of the virus-related proteins, and we were working on the main protease of the SARS-CoV-2. And of course, as almost every crystallographer, we did it using frozen crystals. There was a paper on doing it at room temperature, and they referred to a structure showing that, you know, the very important water was not present in the structure, which was done under cryogenic conditions, and it was present at room temperature structure. And, you know, you looked at the structure, frozen crystals, and there was beautiful density for water. It was just not modeled. So there is a paper which interpreted that structure without looking at it. So, and then of course there are some people who go the other way, and they drown their structures. So this one had about 7 waters per amino acid, and as you can see, a few of them even fit density. Not too many. Okay, so let's look at some other specific problems that we discovered in PDB. Oops, again. Okay, so here you can see a structure at 1 angstrom resolution. And on the left, you can see the original interpretation with the mercury atom in a fairly gorgeous red density, and which means ain't there. And then there is, of course, an automated method of correcting the structures. It's called PDB redo, and they re-refine every structure. But they re-refine, but they don't rebuild them really. So as you can see, the only thing that happened was that right now this electron density for the mercury is really, really beautiful red, much better red, showing that it's even less there. And then when we just did some very simple re-refinement and removed it, everything agrees very nicely. So that's one case. So here you can see a small molecule fitted to something, and obviously that doesn't fit. Unfortunately, that's from one of my structures. I didn't pay enough attention to what my colleague submitted to the PDB. So yeah, you know, you sometimes correct yourself. Now, some people forget to model part of the structure. So you can see in A, there are some water molecules in very nice electron density. And then, you know, PDB redo has just kept everything more or less the same, but it was not a very big deal to just put the missing amino acids and refine it. Again, that's how it was deposited in the PDB and how it is still in the PDB. Now, it's usually fairly good to think about chemistry when you build structures, because it is rather unlikely to have calcium with the nitrogen as one of the ligands, okay, for calcium. And also, by the way, you can, if you look at the temperature factors for this asparagine on the right, you can see that it's very high for oxygen, very low for nitrogen, which is, again, it's the data-based indicator that you have to flip it. And again, we're talking about a very high resolution structure, which is in the PDB. Now, I already came up with the story of occupancies go above 1, so I will not repeat my joke about the cosine, but this is for the atomic resolution structure, and I mean, that's for one of the highest atomic resolution structures of Crambin. And the fact that some of the occupancies are above 1 is the artifact of the refinement of alternate positions of some atoms. However, we know that occupancies cannot go above 1. So this is strictly a refinement artifact. Now, I remember that from time when I was working on neutron diffraction. And there, if you want to refine the occupancies of hydrogens, you have hydrogen and deuterium, they have opposite signs. So you refine occupancies and everything is fine. I found that if we just tried to do the occupancy refinement on the labile hydrogens, all the errors were in there, and that was nonsense. But if we let all the occupancies of all atoms vary, it spread the errors sufficiently that the numbers for particular type of atoms were believable. But, so that is clearly a trick of refinement. But that's not how these models have to be deposited. And of course, that's not how we deposited them at the end. Here, they were just rough model from refinement was deposited, and that's why you have those occupancies more than one. Now, you should believe electron density, even if you know for sure what it is that you have in your crystals. So in this particular case, the authors of the paper believe that they have this nanobios in the crystals, and the only way they could fit it was by postulating two orientations, and it isn't a terribly good fit of density anyway. It was much easier to just say, all right, you either have wrong bottle of the carbohydrate that you put in your crystals, or you confuse your data sets. But if you put trehalose in there, it fits the density perfectly. So this is a structure with trehalose and not with the nanobios. All right? Strictly on the basis of what's in the electron density. Trust your data. Now, here is another case where the authors believe that they had glutamine as a ligand. And you can see on the left so-called glutamine, then you remove this ligand and do a little bit of refinement and get so-called omit map, which is the map calculated without the contribution of that particular residue. And this omit map looks very clear for putting a hippies molecule in there from the buffer. So, that's not very unusual that you expect a ligand and you find your buffer molecule instead. But again, you should be fairly careful in verifying that just because you know that something should be there, don't say that it is there if data say otherwise. And here in the top left panel A, I don't want to go into the gory detail, is the aspirin molecule, which is at the beautiful red density. And in that case, things were really confused with the B factors and such. And when you really think about it, there was no aspirin in that particular data set. And here we come to people who model something with a great degree of optimism, because here you can see the omit map for this particular part of the chain. And as one of my distinguished colleagues once said, given enough parameters, you can fit an elephant. And I think that an elephant would fit here about as well as the coordinates that are actually in the model. So this is kind of real, true optimism of the authors, and We do want to have complete models, but we don't always have enough data to do it. Now, this is a real funny story about PDB. So if you look at the first original deposition, you can see that the R factor was 58%, which is just a tad above random. I guess random would be 57. And everything is wrong with that particular model. So then the author of this beautiful deposition re-refined it using the same data and redeposited, which is perfectly legal because the original author is always allowed to reinterpret his or her own structure. As you can see, there was improvement, but there wasn't that much improvement. And then he decided to do it again. And there is the third model on the bottom. All of them are unpublished. So for the life of me, I have no idea what was the purpose of this particular exercise. So now we have 3 models in the PDB. And we don't know why they are there. And even the final model is of very, very poor density. So that shows you that there are some weird things in there. Now, the 2 other models are sitting in a particular part of PDB for old structures that are withdrawn, because nothing is ever permanently withdrawn from PDB. It's just sent to the archive, so you can look at all of those structures that were right now redeposited. But I don't know for what purpose. Yeah, and then you have to be really quite careful. You don't want the number of reflections used to calculate R3, which shouldn't be ever more than about 1,000 reflections or 5% of data, whichever is less. But some people just don't remember that. But certainly 90,000 reflections, that's a mistake. But that's in the deposited coordinates. So we cannot truly believe everything that we find. We find some interesting space groups. If you look on the right, that it's not in the PDB, that's in the paper that I had on my desk, and you can see that tetragonal space group getting beta of 90.7 degrees. Just have we heard about symmetry here? Yeah. So yeah. You don't get in tetragonal space group 90.7% angle. And there is another thing which we have been fighting with PDB about, and that's the caveat. Now, caveat is a very useful thing. If there is something in the structure that departs from the norm, which does not mean that it's wrong, but it means that it's unexpected or suspicious, PDB can put a caveat into the structure. Now, I remember looking at these caveats, and in one case I found that there was a D amino acid in the chain, and it was, of course, marked because amino acids are supposed to be L, but it turns out that there are cases where there may be an internal catalysis which will change the L-asp to D-asp, and that's what happened, I guess, in that particular case. But in general, caveats are really useful. I have no problems with caveats. I have a problem of where they are. Because in the old-fashioned files, in the so-called PDB legacy files, caveat is just below the title. So a human can just open the PDB file and see immediately that there is a caveat, that there is something funny about that structure. Beware, okay? That's all there is to it. You see here examples of different types of caveats. Right now with MMSIF, it's all buried. Now machine users will have no trouble because you just look for caveat and you find it, and you may do with that particular structure whatever you want, but you know that there is a question. I've been begging PDB to put the caveat on the top page when you access PDB web page, so the user knows that structure has a particular problem that was not resolved during deposition. I will never live long enough to see it done. Okay, and the last subject I want to cover is cryo-EM. And as you can see from this graph, the number of structures by cryo-EM deposited every year is going to surpass the number of crystal structures, probably, if not this year, then probably next year. Trend is very clear. You can also see that the number of structures to be published in crystal structures is still, the fraction is much more than cryo-EM, so people are still writing papers on what they deposited and not just deposited them. But there are, so cryo-EM clearly is catching up with crystallography, but there are some differences. So for example, you can see here on the left that cryo-EM structures are on the average much larger than crystal structures, and there are some theoretical minimum sizes of structures that are possible to determine by cryo-EM, and there isn't a minimum really for crystal structures. And also you can see that the resolution of the structures on the whatever passes for resolution in cryo-EM, and I don't want to go into the details of that, but the definition of the resolution in cryo-EM has nothing to do with the definition of the resolution in crystal structures, but people still compare them because it's a nice number. So you can see that still the resolution for crystal structures is better than the resolution of cryo-EM structures. And when you look at the geometric parameters of crystal and cryo-EM structures, it turns out that geometry is not that different, mainly because the refinement is all done the same way, and the refinement very much drives the geometry regardless of data. But if you find the interpretation of the cryo-EM structures, there is still lots of optimism in fitting, because the median resolution of cryo-EM structures is 3.2 angstroms right now. And, you know, it's sometimes not so easy to fit things at that type of resolution. So one has to look with some degree of caution at the cryo-EM structures. On the other hand, there are some particular cases, and ribosome is the best example, where cryo-EM wins hands down with crystallography, because there are about 600 crystal structures of ribosomes and 1,300 cryo-EM structures of ribosomes, and the structures of ribosomes done by cryo-EM are at higher resolution, the best structures, because they went to right now about 1.5 angstrom, and the best crystal structures is at around 2 angstrom. It's hard to crystallize ribosomes still, and you know, it's a perfect technique for looking at molecules which are big, which are reasonably rigid. So in this case, clearly, ribosomes, for ribosomes, cryo-EM wins hands down. Okay. So, to summarize, usually there are no problems with structures. Sometimes there are. And we really want to know what is good, what is bad. And we hope that when structures are used, prepare data for AI, that the good structures will be used, the bad structures will not be used. And hopefully AI is clever enough to figure it out all by itself. But yeah. And it should be, if authors have the responsibility at the end to do everything. So that shows, that shows what happens when people like us are fighting with PDB and losing our battles. Correcting the record is not easy, okay? And of course, this is mostly members of the Polish crystallographic mafia. The rule of Polish crystallographic mafia is you don't have to be Polish to be member of the Polish crystallographic mafia. And Bernard Rapp, for example, who is Austrian, is the Secretary General of the mafia. And I am capo di tutti capi of the mafia. So,
Thank you very much, Alex. Stop recording.
sure.
And we'll invite questions. So, yes. Yes.
So, we are really considered to be kind of enemies of PDB, and